Hello, and welcome to this presentation related to vibrations. This is part 1 of the lecture. Vibrations is a very substantial topic and also considered a particularly specialised area. And it's not a topic I am particularly familiar with. So for this presentation, the essence is simply to try and outline basic terminology, definitions, and derive essential equations related to vibration problems. To do this, I've just scanned various textbooks and reference sources, and I've tried from these resources to present as best I can a coherent introduction to vibrations that's required at our technician level of study. The mathematics underpinning vibrations and associated analysis can be quite intense and indeed require some specialist knowledge, for example, of solving differential equations. So in parts of the presentation, I've tended to opt for a qualitative analysis as opposed to a quantitative analysis and just overview the findings of mathematical derivations. For more in-depth coverage, I would encourage you to review other more advanced presentations. So the essence of the analysis will relate to mass, spring, and damping systems. And here's a brief overview of part 1 of this vibrations and damping presentation. First, we commence with some underpinning and background knowledge required to understand the analysis that will be outlined within the presentation. We state some terminology and definitions. Qualitatively, we introduce free and force vibrations and also damping effects. Various nomenclature, formulae and SI units are stated for ease of reference. Then we consider damped oscillations of mass spring systems and overview how the appropriate second order differential equations are formed. From this analysis, we will see that there are various parameters that we need to be aware of when analysing damped mass spring systems, and the damping ratio, usually given symbol zeta, is an important parameter. And we outline various damping characteristics. Just note for reference that some reference sources use the Greek letter xi to represent damping ratio, but we'll predominantly be using the Greek letter zeta throughout our various presentations. This part 1 sets the foundation for the further parts of the vibrations in damping presentation. And here are the approximate start times stated in minutes of where the various sections within the presentation commence, hopefully to aid your ease of access through the presentation. These are only approximate start times to the nearest minute. Here's an overview of underpinning and background knowledge that's required to understand the contents of this presentation. Firstly, that you're aware of the spring stiffness characteristic and how to calculate the force from a spring that's being extended or compressed. And also that you're aware of use of dampers and damping effects and how to calculate damping forces when you know the damping constant. We will also refer to simple harmonic motion, and there are various presentations on SHM outlining the derivations of theory and applications of derived equations to various problems. Later in the presentation, we will consider centrifugal forces, that is F equals to m omega squared r, and also you're familiar with sinusoidal forms, such as the sine and the cosine functions, and how to generate these functions from rotating vectors, often referred to as phasors, and that we can resolve forces into components and construct force vector diagrams. Underpinning all of this, of course, is transposition of equations, rearranging equations, and we will also later on solve quadratic equations using the quadratic formula. So that's an overview of some of the underpinning knowledge required to help understand the contents of this presentation. There are separate presentations on all of the above topic areas. Underpinning and background knowledge continued. Referring to a previous presentation related to differentiation applications, we have shown a relationship between displacement velocity and acceleration, it can be found using successive differentiation. So this slide is basically an extract from a previous presentation. If we were to plot displacement x in meters against time t in seconds, we would have a displacement time diagram as shown here. So the curve plotted is defined as x is equal to a function of t. Considering a point on the curve, if we find the gradient at this point, the gradient is actually the velocity at that point. In other words, v is equal to dx by dt, the first differential. If we now plot velocity, v in meters per second, against time t in seconds, we plot a velocity time diagram. This has the equation to the curve v is equal to function of t. If we now consider a point on the curve and find the gradient of that point, the gradient is now the acceleration in meters per second squared. This can be written as a is equal to dv by dt or d2x by dt squared. So the first differential of velocity with respect to time, the second differential of displacement with respect to time. So that kinematic relationship we need to be aware of as we develop our theory related to damped mass spring systems. Underpinning and background knowledge continued here. And just summarising the previous slide, when we differentiate displacement with respect to time, we derive velocity, and when we differentiate velocity with respect to time, we derive acceleration. And just notice for reference the various notation that can be used. For velocity, that can be written as dx by dt, or x with a dot above the symbol, or x dash. Acceleration, sometimes written as d2x by dt squared, or dv dx, or x with two dots above the symbol, or x double dash. Different textbooks tend to use different symbols, and you'll see some of those symbols used throughout the lecture series on vibrations. We're just going to outline some basic terminology that will be used throughout the presentation for your reference. So let's define oscillation. That's any repeating motion of a mass or rigid body about an equilibrium or a mid position, sometimes also termed a mean position. Simple harmonic motion, SHM for short. This is where a mass oscillates about an equilibrium position under a restoring force. This restoring force is directly proportional to the object's displacement from the equilibrium position. Vibration relates to situations where mechanical oscillations or deformations of elastic structures occur, and these can be either free, that's natural vibrations, or force vibrations. Terminology continued. Free vibrations, these occur when a system oscillates under the action of forces inherent within the system itself. The system will vibrate with one or more of its natural frequencies, where the dynamic properties are determined by the system's mass and stiffness characteristics. Force vibrations, these occur when a system is excited due to external forces applied. And here the system is forced to vibrate at the excitation frequency. If the excitation frequency coincides with the system's natural frequency, then a condition known as resonance occurs, and this causes excessively large oscillations to develop, which can be a dangerous situation for our system. Let's consider free and forced vibrations and damping. It's an introduction. So part A here. Free, sometimes termed natural vibrations of elastic systems. So free vibrations occur in an elastic system when the only forces acting on the body are internal restoring forces. In other words, there are no external forces applied. Such vibration can be caused by an initial disturbance of the body from its equilibrium position, and as the body's restoring forces and accelerations are proportional to the displacement from the equilibrium position and always directed towards the equilibrium position, then the body is said to move with simple harmonic motion, SHM for short. If a body held in position by elastic constraints, such as in a mass spring system, is displaced x from the equilibrium position, x shown here, equilibrium position here, by an applied external force and then released, the body begins to oscillate. Work is done by the external force, producing this initial displacement against the internal forces which resist the deformation. Work is stored as elastic or strain energy in the constraints, so when the external force is removed, the internal elastic forces tend to restore the body to the equilibrium position. Assuming no resistance to motion of the oscillating body, all the elastic or strain energy is converted into kinetic energy at the instant the body reaches its original equilibrium position. So from this position here, original displacement, from the equilibrium position to this position here, back at the equilibrium position. But we know from experience that the body will then overshoot the equilibrium position and its motion continues until all the kinetic energy is absorbed and doing work done against the internal elastic forces. In other words, as it moves from here to here. And that's where all the kinetic energy is then converted back into strain energy. So the entire sequence shown above repeats itself and oscillation continues indefinitely, assuming that the system is undamped. Part B here. Let's consider force vibrations. Force vibrations occur when a periodic disturbing force is applied to a body which is elastically constrained. After initial disturbances have died away, the vibration produced normally settles down to what's termed a steady state frequency, which is the same as the forcing frequency. Part C, damping. In both free and force vibrations, damping may be present. Damping forces are caused by frictional resistances to motion of the body and may be external, such as air resistance or fluid resistance, or they could be internal due to relative molecular movement. And these occur when the materials are deformed or strained. Let's review the nomenclature we're going to use, some of the basic formulae and the appropriate SI units. So displacement of our system is denoted as x in meters. The main mass of our system, shown here, capital M, stated in kilograms. Instantaneous time is lowercase t in seconds. Spring stiffness, the symbol K or sometimes lambda, is defined as the force applied divided by the extension of the spring. So that has the SI unit of Newton per meter. Amplitude of our movement, capital A, is in meters. The system's damped angular frequency, that's omega d in radians per second, and the system's undamped natural angular frequency, denoted as omega n, that's defined as the square root of the spring stiffness K divided by the main mass m. That's in radians per second. The damping constant, C, has various units. It can be expressed as newtons per meter per second, or newton seconds per meter, or kilograms per second. Any of those units is acceptable. The critical damping constant, denoted as C suffix C, is calculated from the formula square root of 4 multiplied by the main mass multiplied by spring stiffness K, or that could be written as 2 multiplied by the square root of mk. Again, various units can be used as stated above. The critical damping constant is essentially the minimum damping value that prevents any oscillation. Finally, the damping ratio, often symbol zeta, is used, and that's the damping constant of our system divided by the critical damping constant. And that's a ratio, so that's dimensionless. So that's the nomenclature, formulae and SI units that will be predominantly used when analysing our mass, spring and damper systems. Let's consider damped oscillations. This is the theory for a mass spring damper system when there is no external force applied. So figure 1, shown here, is a diagrammatic representation of a mass spring and damper system. The body of mass M, shown here, supported by a spring stiffness K, shown here, here's the spring, that's assumed to have negligible inertia, is attached to an oil dashpot whose resistance is proportional to the relative velocity. So here's what's sometimes referred to as a dashpot and damper, having damping constant C, diagrammatically shown here. Damped oscillations continued. Let the main mass, capital M, shown here, be given a downward displacement from the equilibrium position and then released. Note this is the equilibrium position shown here. The equilibrium position is the stationary position where the mass is supported by the force in the spring and the force in the damper. At some time t, the mass will be a distance x from the equilibrium position. This is distance or displacement x. The spring force, Fs, is equal to negative k multiplied by x, where k is the spring stiffness. Note that the negative is added because the spring force is acting in the opposite direction to the motion. In other words, the displacement is shown as downwards, so the spring force will oppose the displacement. Its sense will be upwards. So essentially the spring force is acting on the body to restore the body to its equilibrium position. Also, the damper force will tend to oppose the motion. This is the damper force. Again, the direction of the damper force opposes the displacement or the velocity, and is calculated as Fd is equal to negative c multiplied by dx dt. C, of course, is the damping constant, and dx by dt is the first differential of displacement with time, and from our previous work on differentiation, we know that's equal to velocity. As we said, c is the damper constant or damper coefficient. So if we now apply Newton's second law, summation of F equals ma, to the above free-body diagram, we can form what's termed an equation of motion. So on the left-hand side, we have summation of all the forces, with positive displacement x is down Then we have a negative kx spring force, because that's acting upwards. We have a negative damping force, because again that's acting upwards. And that's equal to, on the right hand side of Newton's second law, ma. So there's our mass. And the acceleration is written here in terms of the second differential of displacement with time, so d2x by dt squared. I've called that equation 1 for reference. Notice that the weight force is not included in the balance, and that's because, of course, we are commencing from the equilibrium position. And at the equilibrium position, the weight force from the mass is being reacted by the spring force and the damper. So that's the stable, stationary position for our system. So the weight force will not be included in equation 1, but it's already accounted for in the fact that the x displacement is from the equilibrium position. Damped oscillations continued. I just try and illustrate the application of Newton's second law again here, hopefully to increase understanding. This time I have a mass. This motion is in the horizontal sense, and it rests on a smooth, frictionless surface. So here's the mass, here's our spring, stiffness K, and our dashpot damper, damping constant C. If we consider the free body diagram of the mass, M, remember a free body diagram considers purely the forces applied to the body, to the mass in this case. For positive motion, which is shown as left to right here, we would have the spring force from right to left and the damping force from right to left. So applying Newton's second law, summation of all the forces equal to ma, in line with our positive notation, then on the left hand side of the equation we'd have negative fs minus the fd, and that's equal to, on the right hand side, ma, mass times acceleration. On the next line we know that the spring force fs is actually k multiplied by x. We know that the damping force is actually c multiplied by v, and that's still equal to ma. Now this is an illustration of where second order differential equations can be generated. We have an equation here effectively with three unknowns. We can't solve one equation with three unknowns, but we do know from our mathematical background that there's a relationship we can derive between displacement, velocity, and acceleration. If we differentiate displacement with respect to time, we calculate velocity. If we differentiate velocity with respect to time, we calculate acceleration. So in other words, we can replace this equation here with an equation as a function of x only. So the first term on the left hand side, the spring stiffness term, that stays the same because that is a function of x. But the velocity in the damping force equation can be replaced by dx by dt. In other words, the first differential of x. The acceleration on the right hand side can be replaced by the second differential of x, d2x by dt squared. So now considering this equation, we have one equation as a function of x. The problem is we have effectively a second order differential equation in x, and they are particularly difficult to solve. In fact, usually when I'm delivering this lecture on vibrations, the technician students haven't actually covered the solutions of second order differential equations, and there are various techniques for solving them, such as the operator method or Laplace transforms. But for now, I just want you to take on board of how a differential equation can be formed by applying mechanical principles, in this particular case applying Newton's second law. Damped oscillations continued. Just repeated equation 1 for convenience here. Now the rest of the slide is quite difficult to follow, and it needs some experience in the understanding of solving such second order differential equations in the context of vibration analysis. So I'm just very generically going to show you how equation 1 is manipulated and solved for an equation in terms of displacement. So to progress from equation 1 to equation 2, shown here, firstly equation 1 is divided throughout by m, and then all the terms have been brought to the left hand side of the equation and produce what's termed a standard form for this particular system. So note that this m cancels with this m, So we just end up with d2x by dt squared. So we end up with this expression here being this expression here. Bringing the negative terms from the left hand side to the right hand side makes them all positive now because we're equating our equation to 0. Notice that c divided by m is now written as 2 multiplied by omega n multiplied by eta, shown here. Just note for reference, in this form of the differential equation, the Greek letter xi has been used to signify damping ratio, but generally throughout all of our presentations we're using the Greek letter zeta to represent damping ratio, zeta shown here. And that k divided by m is now written as omega n squared in this equation. And again, if you refer to other reference sources, you'll see that's a standard approach that's used to generate equation 2, which is a homogeneous second order differential equation of the first degree, and now relates to specific properties of our mass spring damper system. And we can see from above, one of the important characteristics will be zeta, termed the damping ratio, and for a spring mass damper system, zeta is calculated from the equation of the damping constant c, all divided by 2 multiplied by omega n, the natural angular frequency, multiplied by main mass m. The solution of the above second order differential equation, equation 2, for damped oscillations can be shown in a general form as stated below. Displacement x is equal to the exponential function raised to the power of negative zeta multiplied by omega n multiplied by t, and that's multiplied by, in brackets, constant b naught multiplied by the sine of omega dt added to constant c naught multiplied by the cos of omega dt. The constants b naught and c naught are found when various system parameters are stated. So to solve this equation 2, the second order differential equation, and produce the final displacement equation here, is actually a fairly complicated mathematical process. And usually when I'm delivering the vibrations lecture, most technician students haven't actually covered the mathematical background to solve such equations. So I'm just showing the displacement equation here without the mathematical derivation. What the displacement equation does show is that there's a rare parameters that we'll need to be aware of when solving vibration problems, and we're going to consider some of these parameters, particularly the damping ratio, on the following slides. And note, purely for reference, I've labelled this equation 3. And I've just included this slide for reference. It shows how we can model various mass spring damping systems by combining exponential functions, and in this case the sine function. So the first diagram, top left hand corner, I've plotted x displacement against t time, and we can quite clearly see this is a sine curve, so x is equal to the sine of omega t. In this second curve here, again x plotted against t, but this time we can see that the waveform is increasing in its amplitude, and that's modelled by the function x is equal to e to the at multiplied by sine omega t. And this third curve here, again x is plotted against t, but this time we can see the amplitude is decreasing as a function of time. And that curve would be of the form x is equal to e to the negative at multiplied by sine omega t. So I'm just showing you that for illustration how combining exponential functions with trig functions, we can also use the cos function as well, will simulate various responses to, for example, mass spring damper systems. So it's quite useful to use these combination of functions to model, to idealize the motion and the output of various mechanical systems. That's just for reference. Let's consider characteristics of damping ratio, usually given the symbol zeta. As we've shown on the previous derivations, damping ratio is a very important parameter of mass spring damping systems. So let's now consider the characteristics of this damping ratio, zeta. And it's shown in the sketches below of displacement x versus time t. So let's consider the situation where zeta, the damping ratio, is greater than 1. This is when a system is termed overdamped. Here, no oscillations will occur, but it takes a long time for the system to return to the equilibrium position. Illustrated by this curve here, we have our initial displacement for the system, but it takes a long time for the system to return back to the equilibrium position when the displacement is equal to 0. So that's the situation when zeta is greater than 1. If we consider a situation where zeta equals to 1, that's considered to be critically damped. So again, there's no oscillations, but the system swiftly returns to the equilibrium position. So here's again our offset displacement. We can find now that there's no oscillations occur, but the system returns quite rapidly to the equilibrium position when x is equal to 0. So that's when zeta is equal to 1. Let's now consider a system where zeta is less than 1. This is now termed an underdamped system. Here oscillatory motion will occur, but the amplitude diminishes with time. So from our initial displacement x, the system then oscillates around the equilibrium position, but notice how the amplitude is decreasing with time, and eventually the system will come to rest. So that's when zeta is less than 1. Let's consider when zeta equals to 0. This is a system that's not damped, sometimes termed a steady state system, where oscillations will occur and has the constant amplitude of motion with time. So for the initial displacement shown here, we're oscillating about the equilibrium position with a constant amplitude. The amplitude remains the same with time. Characteristics of damping continued. And finally, a system where zeta is less than 0. This is termed an excited system. Here the amplitude of the waveform increases with time. So this is a case where energy is added to the system. In other words, it's the opposite of damping. So for our original displacement x, we can see that the amplitude is actually now increasing with time. So in most cases, that's something we want to avoid. So that's when zeta is less than 0. Figure 2 here simply illustrates all the previous damping ratios we've shown individually now on one graph of displacement x against time t. The figure 2 just sketches off the various damping ratios. And here's a further slide showing the various characteristics of damping ratio zeta. Again, on our graph we have a plot of displacement x against time t, and for a displacement input to the system shown with the dashed red line here. Consider the input being due to adding, for example, a mass on the end of our spring damper system, from which we find the equilibrium position, shown by this dashed line. And we can see the various responses depend on the value of zeta. When zeta is less than 1, shown by these three curves here, we have underdamping occur. In other words, various oscillations of the system occurs before finally being damped out. When zeta is greater than 1, shown by these three curves here, we have overdamping. So no oscillations occurring, and we can see the larger the zeta value, the longer the time it takes for the system to return back to the input level. And of course, when zeta is equal to 1, shown by this curve here, we have critical damping. So again, that's just for reference, showing you the various characteristics of damping ratio zeta. So this now concludes part 1 of the lecture related to vibrations in damping. Look forward to seeing you at the commencement of part 2 of the lecture. For reference, here is the bibliography used to help generate this presentation. I hope part 1 of the lecture has been of use to you. Look forward to seeing you for part 2.